Let's continue with the topic of logical effort. So we have already discussed and solved a complete example on logical effort. This is the continuation of logical effort topic. So another question that can be asked is this one: how many stages should a path use? Now this is very interesting, because you may think that if here we have a path from input to output, and if, for example, here we have a gate, for example inverter, then you may think that if we have a single inverter, the delay of the path will be minimal. But it is very interesting that this is not the case. It depends on the capacitance that you are driving. So it depends on the load capacitance. So here is an example. Example is that drive 64-bit data path with unit inverter. So you have 64 C capacitance as a load, and you want to drive this with stages. So for example, you start with a single, you can start with a single inverter, and we already know the formula of delay is this one, that it is n is the number of stages multiplied by f raised to the power 1 by n plus p, the parasitic delay of all the gates in the path. Now if we apply this formula to this one, because we have all the gates are inverters, and for each gate the parasitic delay is 1, so we can replace p by n, because every gate has a parasitic delay of 1 and we have n inverters, so it is equal to n. So the formula becomes n multiplied by 64 raised to the power 1 by n plus n. So this we can solve for example for 1, when n is equal to 1, then this is capital F, not small f. So then f is 64, as this comes from the this load, and we have d, which is equal to 1 into 64 raised to the power 1 by 1 plus 1. So it is equal to 65. So the delay is 65. Now if we increase the number of inverters from 1 to 2, and we use again the same formula, so 2 into 64 by 1 by 2 plus 2. Interestingly, now the delay goes down. The delay is now 18. Okay. If we go and put 3 inverters, then the delay becomes 15, which is the fastest circuit that we can get. The only problem in this circuit is that we have odd number of inverters. So maybe if you are using this as this is your function, maybe this may be my complete microprocessor, and this is one of the pen of microprocessor, which is going to an output outside the chip. So maybe here we have a load of 65N. So you want this path to be fastest possible. So you can put, for example, 3 inverters here. The only problem with these 3 inverters is that you will have an inverted output. So if you go and try for n is equal to 4, the delay is 15.3. So the delay only degrades by 0.3. So you may say, okay, I need a non-inverted output. So you may decide, okay, the delay 15.3 is okay for me, and you can put 4 inverters. So it depends on the designer, what he decides, if he wants an inverted output or a non-inverted output. So this is how you decide the number of stages. Here we have some derivation which I will not go. So without going into the details, how many inverters, for example, consider the same scenario, how many inverters, so these are our extra inverters, how many of them would give the least delay? We want a mathematical formula for that, so that we can come up with an answer. Interestingly, the answer for that is this value, 3.59. So what this means is that in order to if for example, let me consider this scenario. In order to drive this 64-bit load, okay, you want something, you want a number of stages. So how much stages should be there? It should be 3.59. okay, so it's almost 4. So for the fastest delay, you should use 4 stages, and you should equally divide your delay on these stages. Okay, so this is an interesting equation that tells you that 4 number of stages should be used. How sensitive is delay to using exactly the best number of stages? So for example, on this side we have the delay, on this side we have number of stages. So you see here the number of stages are 6 on this point. This point is number of stages 2.4. In between you have the delay, for example 4 is somewhere here. Okay, so for example here. So if you move the stages between this, the delay only changes by 15%. okay, so the original value that we got from equation was 3.59. this was the best number of stages, but we can use 4, okay, because there is only so this the best value was something like 3.59 here. So we can use 4 delay. Now coming back to our original problem that we started with. So we started with the design of a 4x16 decoder. A 4x16 decoder has 4 inputs. Okay, in this case the inputs are available in inverted and non-inverted form. We have 16 outputs. Each of these 16 outputs is driving what is called a register. So every register has, for example, you can say a select line, okay, and one of these 16 bits is connected to the select line. So if the output of decoder, for example, if the output of decoder is 0, then register 0 is selected. If the output of decoder is 1, then register 1 is selected for reading or writing. So this is the functionality of our whole design. So this is the functionality of our whole design. Each word, by word we mean this, whatever we store is 32-bit wide. Each bit presents a load of 3 unit transistors. So from this register file you can read, for example, I can draw it like here. So you have these 32 bit output lines, and each one of those lines presents a 3 unit inverter. You can say that actually the overall load is 32 into 3, which is 6, 9. You can say that all these lines are driving 96 C of load. True and complementary input addresses. Each input drive 10 unit size transistors. And on this side, so if I am, let's say, a 0, so this A0 looking into this decoder, it drives 10 C capacitance. Okay, so Ben needs to decide, number one, how many stages to use, how large each gate should be, and how fast can the decoder operate. Okay, so Ben has to design the decoder. Ben has to design the decoder, okay, and he has to answer these questions. So let's start with the information that is available, and the first thing we want to answer is what is the number of stages that we want to use. So we start with the electrical effort, or this is also called fan out, of the overall circuit, which is 96 as the load at the output. So this is basically C out by Cn of the whole circuit. So C out of the whole circuit is 96 divided by Cn of the whole circuit is 10. So we get a value of 9.6. The next thing is the branching effort of the whole path. Okay, so for that we need to think about the decoder circuit. So the decoder circuit, if I go here, is something like this. It has a level 1 of NOT gates. It has level 2 of NAND gates, and another level of level 3 of NOT gates. So it has 3 levels. Now if you look to the inputs, half of the inputs, so how many NAND gates are there in this level 2? The answer is 16. Okay, and each of these 16 is driven by both inverted and non-inverted inputs. So you can say that half the values are inverted, half the inputs are inverted, and half the inputs are non-inverted. So half of 16 is 8. So the branching effort is 8. Now if we neglect logical effort, so remember that capital F is GBH. So we start with assuming G equal to 1. Okay, why we assume that? Because we have started with the design, and we don't know that we will use NAND gate, or for example we can use AND with an inverter. Okay, so we start with, when we are designing for number of stages, we start with inverters. So always when we want the number of stages, we will assume that all the gates are inverters. This simplifies our calculation. So with 1 we put 1, we put 8, we put 9.6, and we get this value 76.8. So the number of stages from this is according to this formula. So we already determined that the best number of stages is log 4 of F. So we say log 4 of 76.8, which is equal to 3.1. So what this means, that from these calculations, just by knowing our load at the output and our branching effort, these two things, we are able to say that in order to drive this much output load, we need at least 3 stages. Okay, we need at least 3 stages. So let's move forward with our design. Now that's why here we have level 1, level 2 and level 3. This is our 3 stages. But now we insert instead of the NOT gate, we insert our NAND gate, because this is what a decoder uses. So this can be one implementation of a decoder. You can implement a decoder with NAND gate, but you may also implement it with, for example, AND gates. Okay, and there may be another guy who wants to design the decoder with some other gate. Okay, so here is the part of choosing the right gates. But the number of stages, we have determined that the number of stages are 3. Now we can choose different gates for the function we are implementing. Okay, so let's start with the path effort. For example, if we talk about the first stage of inverter, so its logical effort is 1. An inverter has a logical effort of 1 always, because this is a reference. What about the NAND gate? So we already discussed that in the form it was n plus 2 divided by 3. So in this case we have 4 inputs AND gates, so 4, 2, 3. Okay, so that's why it is 6 by 3, and the last stage is again an inverter, so it is 3. So we get the capital G equal to 2, and we already know the branching effort of 8 and H of 9.6. so we put all these things into this equation and we get 154. so now the total path effort or capital F is 154. Now the stage effort is capital F power 1 by 3 because 3 are our stages. So N, capital N is 3 because we have 3 number of stages. So the stage effort is 5 by 3. So what is now the delay? If you remember the equation, it was N F raised to the power 1 by N plus P. This was our delay. We can also write it like this: N F cape plus P. Okay, because this is F cape. So 3 is our N into F plus these are the parasitic delay. First one is the parasitic delay of inverter. Next one is the parasitic delay of NAND gate. So we have 4 inputs. So the parasitic delay becomes for NAND gate becomes 4 into 1. So 4 plus 1. So overall we get 22.1 as our total path delay. Now we need to find the gate sizes. Okay, so we can find the gate sizes. For example, we are interested in finding the gate size Z. So for that the equation was Cn is equal to C out into Gi divided by F cap. So if we talk about Z, so we have a capacitance of 96 is our C out. We have the logical effort of NOT gate 1 and we have F cap of 15.3. so the Cn here is 18. Now we want to find the size of Y, which is our NAND gate. It is again equal to this one, which is 18 is the output capacitances of NAND gate into logical effort of NAND gate was 6 by 3, which is equal to 2. So that's why 2 comes from the logical effort of 4 input NAND gate divided by F cap, which is 5.3, and we get 6.7 capacitance here. And the size of input capacitances is already given in the question, so which was 10. So now we have already determined the all the things that were wanted, that were okay. Now this was one design option, which was this one. We use inverters in the first stage, then we use a 4 input NAND gate, and then we use inverter in the third stage. Okay, but these are so many options. For example, one option can be that we can use a single stage with a 4 input NOR gate, and if you calculate, the delay is huge. Okay, this one is also interesting, that if you use 2 input NAND gate in the first stage followed by NOT gate in in the second stage, followed by another 2 input NAND gate in the third stage, followed by an inverter in the fourth stage. So overall you use a 4-stage design. Interestingly, the delay is reduced from this, so it reduced to 19.7. okay, so it seems that this is the best design. After this one, if you increase the number of stages, you see 5, 6, the delay goes up. So the best one is this one. Okay, so instead of using a NAND 4, if you use a NAND 2 with inverters, you will get the fastest circuit that is possible. Okay, so this is a review of definitions. for different things that we use. So for example, logical effort is G, and path effort is capital G, electrical effort is small h, path effort is capital H, and all these things. Okay, this is the method of logical effort. So first you compute capital F, and you assume, in most of the cases this is easier to start with, that you say all the gates are NOT gates. So you start with G equal to capital G equal to 1. Then you calculate the best number of stages, log to the base 4 of F. Then you sketch the path with n stages. Okay, here you put your own gates, not only NOT gates, but also put your gates that you want to use. Then you estimate the delay. Then you determine the best stage effort, F cap, and then you find the size of the gates. So these are the 6 steps that you have to remember to solve numerical questions related to logical effort. So we have solved 2 very comprehensive examples. In the assignment, I will give you more problems to practice with. Limits of logical effort. So it's like a chicken and egg problem, because you need to compute path to compute G, but actually you don't know G. That's why we start with G is equal to 1. We start with this assumption because it's like a chicken and egg problem. It is a very simplistic delay model, so it neglects the effects of rise times and all these things. Interconnect, it also neglects interconnects, because we say that wires are ideal, but wires are not ideal. Wires have their own capacitances and resistance effects. Maximum speed only. So it gives you the not anything about area or power. So to summarize, logical effort is useful for thinking of delays in circuits. Okay, it is a sort of numerical value that characterizes gates. NANDs are faster than NORs in CMOS. Paths are fastest when effort is approximately 4. So when F is approximately, F cap is approximately 4. Path delay is really sensitive to stage sizes. Using fewer stages doesn't mean faster. So this we have seen that it's not necessary that if you have one inverter on a path that is faster than for example 2 or 3. In some cases, the inverters with the path with three inverters may be the fastest. Delay of a path is about log 4 of f. FO4 means fan out of 4 inverter delays. So it is also used to measure delay. Okay, that for example, if you have 22 something is the total delay, so you divided it with the delay of this circuit. So you divide it with this is FO4. We have seen one example of this. This is FO4. You divide it with the delay of this. Okay, so delay of FO4, and you get the delay in terms of FO4 delays. So basically delay is, and this log 4 of F is FO4 delays. Okay, inverters N2 best for driving large cabs. So remember that NAND 4 was not the best option. So smaller size gates can give you faster delays. So logical effort gives you a sort of language for talking about the delay of circuit. This is the end of logical effort, and this is the end of chapter on delay. I hope that you will practice with several other examples and problems, and hopefully in the assignments try to solve it yourself. These are very important set of problems that you will be asked about in your final exams.